Bismillahirrahmanirrahim. Assalamu alaikum. Today we are going to start the course Computer Organization and Assembly Language. Course code is Csc221. So first of all, I would like to introduce myself. My name is Safdar Hussain Book. I am working as an assistant professor in the Department of Electrical Engineering at Csc221 Institute of Information Technology, Islamabad. Now let's start with the course. So this is the course outline. Basically this course is divided into two sections. These two sections are closely interrelated or interconnected with each other. First section is computer organization, and during this section we will learn about data representation. During this topic we will learn about integer arithmetic, binary representation, floating point representation, and all the arithmetic operations in these number systems. Then the next topic that we will discuss is machine instruction characteristics. During this topic we will discuss about instruction cycles, types of operands, Pentium and PowerPC data types, and so on. The next topic is microprocessor bus structure, and during this topic we will discuss about address, data, control buses, and the registers. The next one is memory organization and structure, and the next topic is addressing modes. So these topics are not limited, or this section is not limited to these topics. We will discuss during the course about the other related topics in more detail. Now the next section, which is related with the previous section, is assembly language. In assembly language, these are the course objectives, like what are the objectives and perspectives of assembly language, introduction to the assembler and debugger, introduction to registers and flags, data movement instructions, arithmetic and logic operations, program control or program flow control, subroutine instructions, stakes and operations during the program, interrupts and interrupt handling, interfacing with high-level languages, etc. Now this course is about what computer consists of, how computer work, how to represent information inside the computer, or how information is represented or being considered or being used inside the computer. This course is about how they are organized internally, how information is organized inside the computer, how design affects programming and applications. The next one is how design affects programming and applications. The last one is programming the machine, how we can program the machine at the lower level by using assembly language. Now we have seen that what this course is about. Now there are some objectives of this course that we have to achieve during this course. All the students who will take this course and they successfully complete this course, they will be able to describe the basic components of a computer system, its instruction set architecture, and its basic fetch, execute, decode, and whole instruction cycle. The next objective is, when the students will complete this course, they can describe how data is represented and organized inside a computer. They will understand the basics of assembly language programming, including addressing modes, subroutines, interrupts, stacks, etc. Last but not the least one is analyze, design, implement, and test assembly language programs. So these are the course objectives that we have to achieve during this course. Now we are going to formally start this course. First of all, what is computing machine, or what are these computing machines? So these machines are ubiquitous, or you can say they are everywhere. They are divided into different classes or different categories. First category is general purpose. So the computing machines who are general purpose, or that are general purpose, like servers, desktops, laptops, PDN, etc. There's another category is called special purpose. So special purpose computing machines include cash registers, ATM machines, games, mobile phones, etc. The third category are the embedded computing machines. These embedded computing machines are like cars, door locks, printers, digital players, industrial machinery, medical equipment, etc. So these computing machines are inside all these equipments, and they are divided into these three main categories. They have their distinguished characteristics like speed, cost, ease of use, how easily you can use, software and support and interfaces, and the last one is the scalability. Now, we have seen computers in everyday life. We use computer. There are two main sections, or two main parts. First one is the hardware, second one is the software. What is hardware? Hardware is electronic circuit boards that provide functionality of the computer. So all these electronic components that are inside the computer, they form this whole machine. Now, to operate this hardware, we need software to make it functioning. Now, what is inside the software? There are programs that consist of sets of instructions that control the system. So these programs, there are sets of instructions that instruct the machine how to operate and how to perform functionality. Now, what is inside the computer? As in the previous slide, we have seen that there are two main parts inside the computer. The computer consists of two things, hardware and the software. Now, what is inside? What are the other things inside the computer? Because we have to go in more detail. This course is about to investigate what is inside the computer, what are the functional components, how do they work. So we have application software, then we have system software, and we have hardware. We already know what is hardware. These hardware or the electronic components, they are interconnected in predefined way or systematic way to form whole computer. And there are application softwares. These application softwares are written in high-level languages. Now we will discuss what are those high-level languages, what are the low-level languages, and so on. And other than this application software, we have system software. So these system softwares are operating systems and compilers. And these compilers translate high-level language code to the machine code so that machine can understand. We will discuss how we can translate high-level language code into the machine language code, and what is machine language code, how does machine understand that code. And in the operating system, we have service code, handling input, output, managing memory and storage, scheduling tasks, and sharing resources, just like everything is done inside the Windows, because Windows is the operating system. Similarly, there is Linux, we have the OS X and Mac. And the hardware, we already know that there are processor, memory, input and output controllers. Now we will discuss the functions of a computer. In previous slide, we discussed there are different categories like general purpose, special purpose, and embedded machines, computing machines. All those computing machines, they have all these four tasks. They perform all these four tasks, not other than that one. So all those computers, they perform first task is called the data processing. They process data and make it in a meaningful format so we can understand. Second is data storage or store data. They store data in some format so that we can retrieve the data after some time when we need that data. The third one is data movement, transferring data from one place to another place, or one storage device to another storage device, etc. Third one is the control. Now this control includes the control inside the machine or controlling other devices. How a programmer view a computer. So a programmer view a computer as, first thing is, we have application programs, then we have high-level languages, and all these application programs are written in high-level languages, and these high-level languages are being translated in the next category is called assembly language. The third category is machine language. Whatsoever is written in high-level language is converted into the machine level language. We will discuss how we convert those high-level languages into machine code or machine language so that microprogram control and hardware can execute those instructions. Here you can see there's a dotted line that represent the boundary. Now these high-level languages above this point are machine independent. They don't care whatsoever the underlying machine is, either it is Intel architecture or MIPS architecture or any other architecture. Whatsoever the architecture is, they don't care. We just write simple program. It's the responsibility of the high-level languages to convert the code into the underlying machine format or underlying architecture format. Now below this line there are low-level languages, and these low-level languages are machine specific. For example, for IBM PC their architecture is different, so whatsoever the program we will write about those machines, that will be for those machines only. Now we will discuss these programmers' view of a computer, or how these programming languages interact with the computer, or how we can program different architectures in the next slides. Now there are levels of program code. In the previous slide we have seen application programs, high-level languages, and assembly language, and macro program, and so on. But here we will see the levels of a program code. We write simple program. As we know that we write some code in C. Here you can see code written in high-level language. So this high-level language we can easily understand. The programmer or the user or the person who is programming writing a program, they can easily understand these instructions. So in the high-level language, the level of abstraction is closer to the problem domain. We know what is the problem, how we can write the code for that problem. For example, if we sort some list, if we search, if we do some other task, if we are performing scientific calculations, if we have mathematical models, and so on. So we can easily program them. And the second thing is they provide productivity and portability. In the previous section, previous slide, we have seen that high-level languages are machine independent. You can write a program, you can compile that program and execute on a specific machine, and so on. You can compile and run program on different machines. So productivity is, it's easy to write. You don't need to go into the details, like the lower level details. We write program without considering the lower level architecture. So portability shifting or moving your program from one computer, one machine, one architecture to another architecture. We can easily write programs. Then the next level of the code is the code written in assembly language. Now there are compilers who directly convert this code into assembly, and then there is assembler who convert into the machine code or binary machine language. Or sometimes compiler directly convert that machine code, that high-level code, into the assembler format or into the binary machine language programs. Now, assembly language is a textual representation of instructions. Even though we will learn about assembly language, so we will learn how to write programs in assembly language. The last level of the code is hardware representation. So inside the hardware, the code is represented in the form of binary digits or in bits, like zeros and one, as you can see here. So these at this level of the code, these data and these instructions, they are encoded and represented in the binary format. Now, there are two terms which are closely related, but they have different definitions, different aspects that we will consider. One is computer organization, second one is computer architecture. Now there is slight difference between these two terms. First one is a computer organization. That is our course that we will discuss during these lectures. So during this computer organization, it represents how components fit together to create working computer system. Means what are the different components that are placed or connected together to form a computer system, a complete working computer system. And it also includes physical aspects of the computer system. The third one is, it is concerned with how computer hardware works. And the architecture, computer architecture, is slightly different from the computer organization. So this architecture defines the structure and behavior of the computer system. The logical aspects means the underlying hardware, means what is the logical gates, what is architecture, and other systems we will learn in the next slides or in the next few lectures. Logical aspects of the system implementation as seen by the programmer. And computer architecture is concerned with how computer is designed, and it provides a combination of hardware components with instruction set architecture. So what is this instruction set architecture? It's the interface between software that runs on the machine and hardware that executes it. So different architectures have different instruction sets. We will learn about the Motorola, IBM, Intel PC architectures, Intel microprocessor architectures. They have their different instruction set. And here in the next slide we will learn what are these instruction set, how we can understand that instruction set, what is inside those instruction set. Now there's a famous scientist and the founder, Intel founder, Gordon Moore. He stated the law, and that is very famous law. He states that the density of transistors in an integrated circuit or an IC will double every year. He stated this law in 1965. So currently the Moore's law predicts doubling of density of silicon chip every 18 months. So Moore originally thought this postulate would hold for 10 years. Advances in chip manufacturing processes have allowed that the law to hold for 40 years, and it is expected to last for perhaps another 10. So what is the principle for the equivalence of hardware and software? How they are equivalent? So anything that you can do, or anything that can be done with the software can also be done with the hardware, and anything that can be done with the hardware can be done with the software. So there is equivalence. Whatsoever computation, whatsoever task that you can perform with the hardware, the same task you can perform with the software also. In modern computers, there is implementation of algorithms that execute other algorithms. Now there is gap between hardware and software. So this semantic gap is the open space between the physical components of a computer system and the high-level instructions of an application. We will see what is semantic gap and how this gap is being filled by different levels or different components. So this semantic gap is bridged at each level of abstraction. There are different levels of abstraction. Now, what is abstraction? The complete definition of abstraction includes the following: suppression of details. So if there are different levels, like level number 1, level number 2, level number 3, level number 1 doesn't know what is at the lower level. It doesn't consider what is at the lower level. It just perform or send the task without considering the actual format of the lower level. So we suppress the details. Each level doesn't know the details of the next level, and it outlines the structure. Third one is the division of responsibility. So each level has its own responsibility how to perform the task, and subdivision of system into smaller subsystems. So these are the abstraction. That is the abstraction, how abstraction is being provided in the microprocessors or inside the computer system. In the next few slides we will see the abstraction inside the computer system. Now, abstraction and computer systems. We can look at a computer as a machine composed of hierarchy of levels. Now, physically, if you see a computer, there's nothing but simply a box, simply a square box or laptop, whatsoever you can call it. Either it's a desktop or laptop, but it's like machine or hardware. So, but internally, when we come very close to the internal functionality, we will see there are different levels. Each level has a specific function, and each level exists as a distinct hypothetical machine, or we can call it a virtual machine. So each level's virtual machine executes its own particular set of instructions, calling upon machines at lower levels to carry out tasks as necessary. Now, abstractions and computer systems. There's a famous writer and famous scientist, Donald Irwin Kenneth. He said, "I really don't think that you can write a book of serious computer programmers unless you are able to discuss low-level details, because without defining or without discussing the low-level details, that is the main objective of this course, to discuss all those low levels, what is happening at all these levels. So without defining those, without understanding those levels, it's really difficult to write a book or to instruct the computer programmers to program the computer effectively and efficiently." Now, there are different levels. Generally, people consider 6 levels. Here we will consider 5 or 7 levels totally, starting from level number 1 to level number 7. Sometimes there are, in different books or different websites, you will find from level 0 to level 5 and so on. So there are, in this course, we will consider these 7 levels in more detail. Like, first level at the lower level, level number 1 is logic get level, level number 2 is microcode level, level number 3 instruction set architecture level or ISL level, operating system level is level 4, fifth one is the assembly level, sixth one higher order language level, and the last is the level number 7, that's called the application. Now these levels can be represented with these labels like AP7 HOL higher order language 6, assembly ASMB 5, OS4, ISA3, MC or machine microcode level 2, logic at level 1, and so on. And each level has its own language to describe tasks performed by a computer. As in the previous slide, we discussed that we have to understand all these levels to effectively program, effectively instruct the computer to perform tasks. Now here you can see from level number 6 and upward, this is machine independent, and from level number 5 and the downward, these are the machine specific. So all these tasks that are performed from level number 1 to level number 5, these tasks are machine specific, and the tasks that are performed at level number 6 and higher level are machine independent. As we have seen in the previous slides, in the programmer's view of the computer. So there are some tasks which are machine independent at some levels, and at some levels the tasks are machine specific. Now at the application level, or level number 7, this level is composed of those programs designed to do specific kinds of tasks for end users, like simulation programs, some programs for banking, finance, simple programs which we write for databases, and so on. And an application may have some sort of programming language associated with it, like macros, shortcuts, for example. So at this level, ideally end users need not to be concerned with the actions and languages associated with the lower levels in the abstraction hierarchy. So this level has provided the abstraction that we don't consider anything, what language we are using, in which language that program is being used, or what language was used to code this, write this program. So at these levels, there's abstraction. We don't know what is the underlying hierarchy or underlying level which is performing all these tasks. We just send the instructions. For example, in the Excel or Word, you write something, you don't know how these instructions are being sent at the lower level to the machine to perform all these tasks. Now at the second level number 6, that is called the higher order language level. Now this higher order language layer is the layer of abstraction at which most programmers operate. Now this is the level where programmers write program to develop applications, and those applications are being executed over the machines. So this level number 6 is the layer or language layer where programmers operate or programmers work. Applications are typically written in higher order languages. Higher order languages are characterized by portability across the platforms. So the program that you are writing or the application that you are writing that can operate on different machines. Relative ease of use. So these applications are these higher order languages. They are very easy to understand, easy to program inside those higher order languages, and relatively high level of abstraction requiring translation of program code prior to the execution. So we know in C we write some statements, we can understand easily all those statements, but we don't know how compiler convert that program in a machine level code or microcode level so that that code can be executed on the machine. Now the level number 5 is the assembly level. Now at this level, assembly language level is an intermediate step between higher order language and the machine language of a particular processor. Now the programs at this level are usually compiled to level 5, then translated or assembled to machine language. Source code can also be written in assembly language. Level number 4 is called the operating system level. So at this level, the operating system is responsible to perform tasks related to multi-programming, including memory protection, process synchronization, device management, etc. The operating systems were originally developed for multi-user systems, but even more single-user systems utilize an operating system. Compilers and assemblers are also considered system softwares. So this is the level number 4. Now we will move to the level number 3, 2, and 1. So the level number 3 is called the instruction set architecture level. Now we will discuss this in ISA or instruction set architecture in more detail in the coming lectures, because that will be the core of this computer organization section. And that instruction set architecture will also be considered in the assembly language, because without understanding the underlying architecture or instruction set architecture, it's really difficult to program any machine in assembly language. So the instruction set architecture or machine language level consists of the set of instructions recognized by the particular hardware platform. So there is a set of instructions that are particularly recognized by the architecture. For example, Intel architectures, they have different set of architecture or instruction set architecture. In the IBM, Motorola architectures, they have different instruction set architectures. We will discuss there are different instruction set architectures, how they are divided into two main categories like CISC and RISC. We will discuss in more detail. But at this point, at this abstract level, these instructions at this level are directly executable without any translation, because these instructions are directly understandable or directly executed over the machine. Now we will discuss about the level number 2. This level is called the microcode level. As we discussed in the previous slide or few slides, that microcode is the representation of the code or a program or data in the binary format in form of zeros and one, or machine instructions, machine language, or micro instruction. So the micro instruction or control level is the level at which the computer decodes and executes instruction and moves data in and out of the microprocessor or the processor. So processor's control unit interprets machine language instructions, causing required actions to take place. Now these are the actual signals or binary instructions that are being carried out or executed by the machine or computer system. This is the lowest level, or the level number 1 is called the logic gate level. So this level is the actual circuit that is performing or that is executing all those instructions. So this level, at the digital logic level, consists of physical components of the computer system, the actual electronic gates and wires, which form this whole level. So Boolean algebra and truth tables can be used to describe the operations at this level. So this level is the lowest level, which is called the actual hardware level. Now we'll see, you have seen this computer. This is the very old figure, but it describes mostly all the components. So this is the complete anatomy of a computer. You can see monitor, you can see modem, system unit, mouse, speaker, printer and keyboard. Now we will see how functions are being performed inside a computer. This is the functional view. Here is the data movement apparatus, or the device that controls the data movement, or the component that controls the data movement. Then we have control mechanism. This unit controls whole data flow. And then we have a storage facility, we have data processing facility. So all these are the abstract level components of a computer. Now for example, if we need to move data, for example, from keyboard to screen, when you type something you can see the data directly on your screen. So that data comes in this direction. So this data movement apparatus or data movement controller, it receives data from keyboard, sends through this control mechanism and back to the screen. The next operation that you will see here is the storage. So this data movement apparatus, which is responsible to move data from one place to another place. For example, if we want to store data, if we download something from internet, what we do, we receive data and we store data in hard disk or somewhere else. So the lines are from where we receive data are the components which are responsible to provide connectivity and wires and so on. So we receive data, control mechanism send this data back to the storage facility. So data is stored in this storage facility. The next one is processing from or to the storage, like updating Word or Excel file. For example, if we have file, Excel or Word file, which is stored in the hard disk, if we want to modify, if we want to update, if we want to make some changes in that file, what we do, first we retrieve that file from the data storage facility back, and control mechanism receives this retrieves this file and sends to the data processing facility. After making some modifications, again that file is sent back to the data storage facility. So these are the normal tasks that are being performed by the computer. Now this other task is processing from the storage and to the input and output device. Now we process some data which is already stored inside the storage facility. So we process this data. First, the control mechanism retrieves this data and sent to the processing facility. Next, this data is being sent to the I/O devices. So here is the input out. Here are the input or output devices. So these were the main operations of a computer system. Now we will see the more detailed view of this computer. So this is the block diagram, and in next few slides we will see in a more detail what is inside the computer, how these components are interconnected to provide all those functionalities like receiving data from input device, send back to the output device, receiving data from input device, send through some data movement apparatus or data movement facility, data movement path through this control unit, and control unit controls all this data flow, send back to the storage or receive data from storage, retrieve data from the storage, process data and again send back to the storage, or some examples like we have seen, retrieve data from storage and process, then send to the output device or send to some other devices. Now all these functionalities are being performed in this block diagram. Now this is the more detailed view of the computer. First thing is the central processing unit, which is called CPU. There are input devices and there are output devices and there are storage devices. At the center is the memory. Now here you can see there's a direction between CPU and memory. There's a bidirectional arrow, means data can flow either from memory to the CPU or CPU to the memory. And here you can see from input devices there is only one directional or unidirectional arrow. So data just flow from input devices to memory, and maybe from memory to CPU, or maybe from memory to output devices, maybe from memory to the storage devices. But as far as the input devices are concerned, data just flow from input device in one direction towards the other components in the computer system. Now here you can see storage devices and memory. There's a bidirectional flow, so there are storage devices and there's memory, so data can move in between these memory and storage devices. And there's a unidirectional arrow between memory and the output devices. Now we will see the difference between this memory, what is difference between this memory and the storage devices. These two things are separate, and we will discuss in more detail about what is memory and what are the storage devices and so on. Now we will just go in more detail. In previous slide you have seen only 5 components: central processing unit, input devices, output devices, memory and storage. Here the lines which were interconnecting all those 5 components, they are being separated. So again we have the processor, the same processor, or you can call it CPU or central processing unit and so on. There's also a memory. We have the one component called the IO subsystem or input output subsystem, and we have input devices and output devices, so we call them IO devices. So we combine those 2 components, input devices, output devices, into one box to show that the data flow from between here. Now these lines show 3 buses, or address bus, data bus and control bus. So these buses are nothing but simple conducting wires which connect memory with the microprocessor and the input output subsystem, which provides control or interface between the input and output devices. Now one thing which is more important to notice here is the direction of all these buses or all these conducting wires. You can see here this address bus is unidirectional. It flows from microprocessor to the memory or from microprocessor to the input output device. We will discuss for what purpose this address bus is being used. The next bus, or the next conducting line, which carries information, signals, whatsoever you can call it, is called the data bus. So the next bus or the next conducting lines are called the data bus. This data bus carries data in between microprocessor, memory and input output devices. Here you can see the direction of this bus. So data can flow either from input devices to the memory or to the processor, from processor to memory, from memory to processor, and so on. Even from processor to the output devices, or processor to memory, and etc. But the third one is called the control bus. This control bus is unidirectional, so the processor control information flows from processor to the memory and also from processor to the input-output subsystem. So these are the three buses. We will discuss in more detail about these three buses in the next few lectures, when we will discuss about the computer organization and the flow diagrams and so on, and when we will discuss about the computer organization, how data flows, how instruction data. So in next few lectures we will see about all these control bus, data bus, and address bus, how data flows between processor, control data, address data, and actual data flows between processor, memory, and I/O subsystem. So this is the more detailed view of the computer. So the processor has been magnified. Here you can see this processor has three main sections. One is called the control unit, second one is called the arithmetic and logic unit, or called ALU. The third section is called registers. Now these three sections form a complete processor, and there is a data path which connects arithmetic logic unit and registers. So there's a data path, how data flows between these, the connectivity between ALU and the registers. So this is the complete view, detailed anatomy of a computer. So we have central processing unit, CPU, there's control unit, data path, and we have common bus. This common bus includes address, data, and control, and we have memory, program storage, data storage, input output devices, and so on. So inside the central processing unit, or CPU, so the upper part, or control unit, it decodes and monitors the execution of instructions, and it controls the flow of information inside the CPU, memory, and the I/O devices. So whatsoever the information flows between CPU, memory, I/O devices, it controls everything. Just like in the Intel i7 or Core i7, there's a system clock. It's 1.6 gigahertz up to 2.8. It has 6 MB L3 cache and so on, and there it maintains a register called the program counter and so on. So this control unit basically controls all the operations inside the computer. And the next one is the arithmetic logic unit and registers. So arithmetic logic unit performs all the arithmetic computations and logic evaluations or logical operations. These registers are the registers inside the CPU, store location inside the CPU, like they are very small, like 32-bit or 16-bit address, 16-bit storage locations. They can store 32 bits or 16-bit, 8-bit information inside the register, inside the CPU or central processing unit. So these 32-bit or small memory location inside the CPU, they can either hold data, address, or any instruction which is being executed by this microprocessor or central processing unit. So we have seen the common bus. So common bus, there are three buses: address, data, and control. So the bus is nothing but a group of conducting wires that allow signals to travel from one point to another point. So there are three classes or three divisions of these conducting wires. first division or first set of conducting wires is called address bus. So this address bus is used to locate data inside the memory or locate the input or output devices. If we want to address data inside the memory or inside the output to the output devices or from the input devices, if we want to locate any device or any location inside the memory, these buses or these conducting wires are being used. The next set of conducting wires or bus is called the data bus. It carries data in and out from CPU. So whatsoever data goes to the CPU, comes from the CPU, is being carried out by this data bus. The third set of these wires is called the control bus. It controls the operations of the central processing unit and the whole system. So memory is one of the major components inside a computer system. We know that memory stores program and data. So there are two types of memory. One is called random access memory, and another one is called read-only memory. So RAM is a volatile memory. It cannot retain data without power, so it needs power to retain or to hold data, and it allows the processor to read and write into any location on memory chip or inside the RAM. On the other hand, ROM or read-only memory is non-volatile, means when power is removed, then reapplied, the original data will still be there, and ROM can only be read, cannot be written to by the processor. In some types of ROM, we can also write or we can reprogram those memory. Now we have seen memory, but we will see in more detail. If we want to access, if we want to store data inside the RAM, if we want to receive data or retrieve data from the RAM, how these operations can be performed, like reading data from the RAM, writing data inside the RAM, or reading or writing anything or any data in the memory, how we can do that. So here you can see the different components of the memory. Like this memory has different boxes. These boxes are the storage locations. So these storage locations can be 8-bit, 16-bit, 32-bit, or 64-bit. So there are addresses. There are one component is the address. So here actual data is being stored inside this section, and these are the addresses which are being used to access those memory locations. If I, for example, if we want to store or we want to access data like A0 from 2001, because A0 or this hexadecimal data is stored at memory location 2001. So this memory location is represented in hexadecimal format. In the next few lectures we will see how data is being represented in hexadecimal, binary, and other formats. So inside memory, data is stored at different locations, and these locations can be accessed by or accessed through these addresses. So a memory in a microprocessor stores data in binary format or in the form of zeros and ones. So to retrieve information, the microprocessor assigns addresses to the location. Each location stores 1 byte of data. As I told you that if we want to access data from the this memory location, so we will use this memory location to access this value or the data which we have stored at that location. The third component are called the I/O devices. So in the I/O devices, there are input and output devices. These are very common examples of input devices. Here you can see keyboard, mouse, mic, like light pen, these pointers that we are using. So these are called input devices. For example, right now I'm writing something, I'm going to input data inside the computer and so on. So these input devices allow computer user to enter data and programs into computer. So we use keyboard, mouse, mic and so on. The second is the output devices. So these devices display the result of computation, whatsoever the information that is processed by the microprocessor is being displayed in by these output devices. Like we have 7-segment displays, we have LCDs, we have multimedia projectors, we have printers and so many other devices. Here in this slide there are few devices which are being shown here, but this list goes on. So now we will move toward the next section, that's called the assembly language. Now before going to discuss anything about assembly language, we have to ask few questions, few very important questions, just like what is assembly language and why do we need to learn assembly language, what is the purpose, what is the main objective, and what is machine language. If we want to learn assembly language, then what is machine language? How is assembly related to the machine language? What is the relationship between assembly language and machine language? Either they are same, either they are different. What is an assembler? How is assembly related to the high-level languages? And is assembly language portable? Is it possible to execute a program on different architectures which is written in assembly language and so on? So these are the questions that we will discuss in this section of the course. Now in previous slide we have seen the hierarchy of languages, the programmer's view of the computer system. Now here we see these hierarchy of languages, like we have application programs and we have high-level languages, then we have assembly language, we have machine language, and then so on at the microprogram control and hardware. So the programs written in high-level languages, they are translated into assembly language or maybe directly to the machine language and so on. So from here we are not concerned what is happening above, because now we will consider the assembly language. We will learn what is assembly language, how we can program a system in assembly language and so on. But you can see machine from here, assembly language, the programming is about the machine specific. Whatsoever the underlying architecture is, we will program that architecture, we will write program solely for that architecture. So what is assembly and machine language? Machine language is native to the processor, is directly understandable by the processor, so it can directly be executed by the hardware. So the instructions in this as machine language, they are in the form of binaries, in form of zeros and ones. On the other hand, assembly language is a programming language that uses symbolic names to represent operations registers, and memory locations. Now there is difference between assembly and machine language. So in machine language, the instructions are in the form of zeros and ones. In assembly language, there are symbols or there are symbolic names that are assigned to the instructions, the registers, operations, and the memory locations. So assembly language is slightly higher level language, slightly higher, not higher level language, but slightly higher, so that a user, experienced user, can easily understand. In assembly language, readability of instructions is better than machine language, because in machine language, instructions are represented, instruction or data are represented in form of zeros and one. So it's really difficult to read instructions. However, in assembly language, it's really they are in readability format or easily readable. In assembly language, one-to-one correspondence with machine language instructions. Assembly language has one-to-one correspondence. Whatsoever instruction that you are writing inside the assembly language, there is an instruction, same instruction or zeros, form of zeros and ones inside the machine language. So all the one instruction in assembly language has some representation or some form to perform that task inside the machine instructions or machine language instruction. Now there are some other components that we have to discuss beside this machine language and assembly language. That there are some assemblers. We will discuss in more detail about assemblers. So these assemblers are being used to translate assembly language to machine code, or code which is written in assembly language into the machine language. And there are other components like compilers. These compilers translate high-level programs to machine code, either directly or indirectly via an assembler. So here you can see in the next slide that the relationship between the compiler and assembler. So from high-level languages, sometimes compiler directly convert the code into machine language, so the program can be executed over the machine, because machine language is directly understandable by the hardware. On the other hand, the programs written in high-level languages are compiled and converted into the assembly language, and we need assembler to convert that assembly language into the machine language. Instructions and machine language. Each command of a program is called an instruction. It instructs or directs the computer what to do. So as you have seen in higher level languages or other languages like in C, Java and other languages, that we write some program, we write some statements or instructions. These instructions perform some operations. So these instructions instruct or direct the computer what to do. These computers only deal with binary data, hence the instructions must be in binary format, like in zeros and ones. The set of all instructions in binary form makes up the computer's machine language. This is also referred as the instruction set. So the instructions inside the machine language, they are in the binary format. So this machine language has all the instructions in binary format in form of zeros and ones, and they have complete list of instructions that can be executed over a machine, and that complete list is called the instruction set. Now it is not like 1000 instructions, 2000 instructions, 3000 instructions. As you have seen in assembly language, there are different functions, different statements, and there are different formats and so on. But here in machine language, we have limited number of instructions, like hundreds, like only in hundreds, not in thousands. And that complete list of instructions that are directly understandable by the machine is called the instruction set. Now, instruction fields. Each instruction is divided into two main parts or two sections. So machine level instructions usually are made up of several fields. Each field specifies different information for the computer. There are two main fields, opcode and operands. The opcode field stands for the operation code, and it specifies the particular operation that is to be performed. So each operation has its unique opcode. For example, if you want to add two numbers, if you want to move data from one register, one location to another location, if you want to load data from memory, save data to the memory, or store data to the memory, each operation has a specific opcode which is being used or which is understandable by the machine to perform that task. The second field is called the operands field, which specify where to get the source and destination operands for the operation specified by the opcode. Now, for example, if an instruction performs addition of two numbers, so these two numbers, what are these two numbers, or from where we have to get these two numbers, or either these two numbers are available inside the memory or so on. So operands specify this the source and destination. From, for example, if we add two numbers and store somewhere else and so on. In case if we load data from memory location, then we have to show the source, from where, from which memory location we have to load, at which memory location we have to store, and so on. So we have to specify source and destination and all that data which is being performed, on which operation is being performed, is specified in this operands field. So the source or destination of operands can be a constant memory or one of the general purpose registers. So it can be memory location, it can be a constant, or it can be a general purpose register. The registers, as we have seen in the previous slide, are small memory locations inside the CPU. Translating languages. For example, in previous slide we have seen we have higher level languages, we translate them into the lower level and so on by using compilers, we use assemblers. So we have to translate those languages, instructions from different languages into the machine language, so that the computer or the underlying hardware can easily execute. Here is an example. For example, in English, the sentence is D, or the statement is D is assigned the sum of A times B plus 10. So the result of A multiplied with B and added with the value of 10, and the whole complete result is being stored inside D. So this is the statement in English language. So if we convert this English language statement into the high level language, how we can do that? For example, if you consider the case of C, then we will write like this one: D is equal A multiplied by B plus 10 and so on. Or if you consider any other language, so we write A multiplied by B plus 10. So Inside the assembly language, we have to use different instructions like move, multiply, add, and move. Like there's a value A which we have to move into the some registers. Then in the accumulator or other registers we will discuss in more detail. So then we multiply, and again the result will be stored somewhere in the accumulator, inside the accumulator. And then what we do, whatsoever result was inside the accumulator, we add 10, and in the end what we do, we transfer or move data from the accumulator to the D. So there are multiple instructions, like about 4 instructions to perform this task, which was performed in one statement in high-level language, and the task that was mentioned in the English language. So these same 4 instructions, there is one-to-one instruction inside the machine language. So this is the example of Intel machine language, and actually here they are not in the binary format, they are in hexadecimal format, but we will learn how to convert this hexadecimal format into the binary format. But here you can see inside the machine language we have A100, 40400 and so on, that represents the Intel machine language instruction to move data from A register or from A to the some register like accumulator register or some other registers. So all these statements or any statement in high-level language is translated typically into several machine level instructions. The example is in this slide. So one instruction, D is equal A multiplied by B plus 10, is converted into 4 instructions inside the assembly language and 4 Intel or 4 machine instructions. So this is the example of translating between the languages. So there's a mapping. So as in the previous example, previous slide, we have seen how we can map, how we can convert high-level language into the assembly language. So there is a mapping between high-level language and the assembly language. So translating high-level language programs to machine language programs is not a one-to-one mapping. As in the previous slide we have seen, each assembly language instruction has its corresponding machine language instruction. But here in high-level languages, it's not one-to-one mapping. So for one instruction there can be multiple instruction inside the machine language, and a high-level language instruction usually we call them statements. We don't call them instructions. So a high-level language instruction will be translated into one or more machine language instructions. As here you can see data movement instruction clause, like data movement A is equal 5 in C, and assembly language we use move 5 A comma 5, and arithmetic or logical operation like B is equal A plus 5. So this is a very simple operation. So this single operation in C can be written like this one. So in assembly language this operation is written like move A into the AX, add 5 with the AX, and move whatsoever the result is inside AX to the B. Control flow, there's like go to some label. In C language there's one instruction. In assembly language is called jump instruction. There are other instructions for control flow. So the thing is, in C language there can be one instruction or one statement. This is converted in assembly or the machine language into multiple instruction to perform the similar tasks. There are some advantages of high-level languages. So the first at the top is program development is faster. They are handy. It's very easy to write a program because the code is more compact. We don't consider what is the underlying architecture. We just write a program in the high-level language to in few instructions to perform the tasks, and you have seen that for that single instruction there are multiple instructions in assembly language and also in the machine language. So it's easy to is fast to write a program or code inside high-level languages. The second advantage is program maintenance is very easy. It's easy to maintain a program. The same reasons as we have discussed above. And programs are portable, contain few machine-dependent details, can be used with little or no modifications on different machines. So whatsoever the program that you write for one architecture, that can be easily moved to be executed on other machine or other architecture. It is the responsibility of a compiler to translate it to the target machine language. So whatsoever you write in C or other languages, like in Java or some other languages, compiler is responsible. Either you want to program for Intel architecture, for other architectures, compiler will automatically translate the program to the respective machine language formats. On the other hand, assembly language programs are not portable. So assembly language is not portable, or it's very difficult, extremely difficult to port a program which is written in assembly language to other machines. Now, one of the questions is why we need to learn assembly language. The main advantage or the main objective to learn assembly language is the accessibility to system hardware. We are programming the hardware directly. We know if we know that system and its components, assembly language is more closer to the system, so we can directly program all those components. So assembly language is useful for implementing system software, and it's also useful for small embedded system applications. Space and time efficiency, because we can easily understand sources of program inefficiency, where program lacks in efficiency, execution speed, and so on. So we can increase the efficiency of the program. Tuning program performance, we can modify the program, or we can, after analyzing the deficiencies or inefficient points inside the program, we can tune them to make it more faster, to increase the program performance. And we can write a very compact code, because the code which is converted by the compiler may not be that much compact. We can write a new code inside the assembly language that can be more compact and more efficient. Writing assembly language programs gives the computer designer the needed deep understanding of instruction set and how to design one. At the same time, it enables to write compilers for higher level languages. So we need to be expert with the machine language. Assembly language programming provides this experience. If you are very good assembly language programmer, then you can write your own compilers for the high level languages. So assembly versus high level languages, we are going to summarize. High level language programs are machine independent, they are easy to learn, easy to use. On the other hand, assembly language programs are machine specific. It is the language that processor directly understands. Tools for assembly language program or assembly language programming. We need different tools to program in assembly language. One of them is assembler. These tools are like softwares that are needed for editing, assembling, linking, debugging assembly language programs. The more important tool is called the assembler. What is an assembler? An assembler is a program that converts source code programs written in assembly language into object files in machine language, because we have to convert our code into machine language. So this assembler converts source code programs in assembly language into the object files in machine language. There are so many popular assemblers. They have been emerged since last several years for Intel family of the processor, which include turbo assembler for Borland from Borland, and then net-wide assembler for both Windows and Linux, and GNU assembler distributed by the free software distribution. There is also one assembler called the macro assembler for Microsoft. It's called the MESM or MESM. We can use either turbo assembler or macro assembler from Microsoft. It depends on your convenience which one is best. So we will use mostly macro assembler, and sometimes I will give you the introduction about the turbo assembler and so on. So we need also linker and libraries. So we need a linker program to produce executable files. So this linker program combines your program's object file created by the assembler with other object files and link libraries and produces a single executable program. So this program is in an executable format, so we can directly execute this program over the machine. So we need linker and libraries. So this linker combines object file with other libraries to perform a single executable file. This is a complete process, assembling and linking process. So we have source file here. Assembler converts it into the object file. Simply what we do, we have some libraries and we write object file. Linker combines these library with one object file and provide the executable file. In other format, it is possible that we can have multiple source file. Assembler converts into multiple object files. This linker combines all these object files and along with the libraries to produce or provide one executable file. So a project may consist of multiple source files. Assembler translates each source file separately into an object file. Linker links all the object files together with the link libraries, and the output or the product of this linker is executable file which can directly be executed over the machine. Now we summarize what we learned during this discussion in this lecture. First of all, we have seen the complete anatomy and the functional view of a computer, that what are the components of the computer, like CPU, memory, input devices, output devices, and storage, and so on. Then we have seen the functional view of a computer, how data flows from input devices to the memory, from memory to the output devices, and so on. The next thing that we learned during this lesson, during this lecture, how different components fit together to create a complete working computer system. The third thing that we discuss in this section, in this lecture, is a computer system can be viewed as a layered system, or in form of layers. So the programs at one layer are translated or implemented or interpreted by the next lower layer. And then we also learn about assembly language, that it helps you learn how software is constructed at the lowest levels. Assembly language has also one-to-one relationship with the machine language, and we need assembler program that converts assembly language programs into machine language. And then we also learn that we need also linkers that combine individual files created by an assembler into a single executable file. Thank you so much, and Allah Hafiz.